Taking a look at the Doppler effect, the first thing that you need to do is you should look up a couple videos about the Doppler effect. This is one of a train coming through a station, and what you'll notice is as it goes by or a car goes by, it's a higher pitched as it comes towards you and a lower pitch as it goes away. So don't get confused. It's not how loud it is. The Doppler effect is more about the note that it's playing or the pitch. My personal favorite Doppler effect video is this one, where if you Google Doppler effect on YouTube, you'll see this car, and as it's going towards the person, the waves on the right are getting bunched up or getting closer together. And when the person's on the left, the waves are farther apart. And so that's the Doppler effect. So the Doppler effect is the apparent change in the frequency of a wave caused by the relative motion between the source of the wave and the observer. And what that means is that either object could be moving, either the person listening to the sound or the thing making the sound, or the light wave. And if they're getting closer together, it's going to be a higher frequency. And if they're getting farther apart, it's going to be a lower frequency. This is the equation for Doppler effect. There's a few different ones. This is the one that I prefer. So on the left, you have the frequency of the observer. And then on the right, you have the frequency of the source. And V, just the black V, is the speed of light or the speed of sound, whatever you're looking at. And then V0 is actually the velocity of the observer, and Vs is the velocity of the source. Now, if you notice, to the right is positive and to the left is negative for both the observer and the source. But when the observer goes in the positive direction, it gets closer to the source. And when the source goes in the negative direction, it gets closer to the observer. So if you draw out a picture like this and you just pay attention to which one's going in the positive and negative directions, then the equation makes perfect sense. And the velocity of sound is 343 meters per second. So what this means is the velocity of the observer is going to be positive when it's going towards the source and negative when it's going away from the source. And for the source of the wave, for example, the ambulance making the sound, it'll be negative if it's going towards the observer and positive if it's going away from the observer. And the observer is going to be what's listening to the sound. And of course, if something's not moving, then you're going to put a 0 for that velocity. So in the equation, you might have noticed that the top symbol is going to be when they're going towards each other, and the bottom symbol is when they're going away from each other. And you could have both of them moving at the same time, either towards each other or away from each other or in the same direction. So just be really careful about what is a plus and what is a minus. So when is it positive or negative? Okay, so when it's getting closer, the observed frequency is going to increase or become a bigger frequency. And when it's getting farther apart, the observed frequency is going to get smaller. So what's going to happen to the fraction? Well, let's look at this. So this is what you're observing. If things are getting closer together, you need that number to get bigger. Well, the source, this is going to stay the same. That's the frequency of the source. So if they're moving towards each other, what can you do? Well, the top, if I need the frequency to get bigger, the observed frequency to get bigger, then I need the fraction to get bigger. Well, the top number could get bigger, or the bottom number could get smaller. And either way, that's going to make the fraction bigger than 1. And if the fraction is bigger than 1, then the observed frequency is going to be bigger. And if they're going away from each other, then the top number would need to get smaller, or the bottom number needs to get bigger to make that fraction less than 1. And so that is how we can also think about, is the frequency going to get bigger or smaller for that observed frequency? Again, the source of the wave is not changing frequency. It's the observed frequency. Your horn is not going to make different sounds depending on which way you're driving. If you're in the car, your horn sounds the same the whole time. And just reiterating, the Doppler effect or the observed frequency, like the color of light or the pitch of a sound, can be caused by the motion of the source, the motion of the listener or observer, or both moving at the same time. Now you're going to take a look at sample problem 3 and sample problem 4.